This is the second lecture about geometry. It is a natural successor to the first lecture on analytic geometric representations. We now turn to the qualitative structures, and we want to impose axioms on the qualitative structures such that we can prove representation theorems in terms of the analytic representations. The material to be covered here is, as in the case of the first geometric lecture, substantial and wide-ranging. It'll be possible only to hit the high points and not to go into a great many details that are of considerable interest. There is other material in the chapter that I will mention at the end, if we have time, concerning applications. We have a substantial section both on applications in physics and also one in the theory of perception in psychology. But the focus of the lecture will be to retrace the concepts covered in the first lecture on geometry, but doing it from this different standpoint. This means that we'll mainly concentrate on the following topics. I want to start with order on the line, looking at the generalizations of simple ordering as reflected in the real number. Secondly, I want to talk then about projective geometry, in particular the two-dimensional projective plane. Third, projective space. Intuitively, we'll have in mind 3 dimensions, but for some applications, it'll be useful to have results on more than 3 dimensions. Then we turn to ordered geometry. Ordered geometry as such was not mentioned in the previous lecture. The important special general case of this is affine geometry. We get affine geometry out of ordered geometry by restricting the axioms. And then we further specialize affine geometry to get the important cases of absolute, Euclidean, and hyperbolic geometry. In terms of these classic parts of geometry, or types of geometry, I'm omitting in this lecture elliptic geometry, which is discussed in the chapter. The reason is that it doesn't fit as easily into this categories and doesn't follow directly from the material covered in the first lecture. Notice that the main emphasis then will be on projective geometry, affine geometry, and Euclidean geometry. The last topic I want to at least spend a little bit of time on is a famous problem in the foundations of geometry, the Helmholtz-Lee problem of the nature of space. We'll have time at least to say something about it at the end. So let's turn then to the generalization of a simple order. Remember, a simple order is reflexive, anisymmetric, transitive, and connected. And the natural representation of it is in terms of the numerical relation equal to or greater than. In the case of geometry, think for the moment of a one-dimension line, and the one-dimensional case will be of interest because when we restrict ourselves to the one-dimensional case, the order along the line will be invariant in everything from affine geometry up that I want to discuss first, namely the classical case of betweenness. Now, in geometry, if we think of a line, we don't have any natural choice between this direction and that direction. But we do have a completely natural and intuitive characterization of when one point is between 2 others, for which we use the notation in vertical bars as shown below. That is, B is between A and C. Grammatically, it's awkward in the sense the natural thing is to say B is between A and C. And both in terms of the picture and notation, we actually want to write it with B being shown between and not as in the grammatical form. Because of the wide use of betweenness, it'll be useful to state the elementary axioms for this ternary relation. It's probably the most important ternary relation that is not an operation. Of course, binary operations that we consider in measurement so much are special cases of ternary operations. Betweenness is a good example of a ternary operation that is not a binary operation. And as such, it's probably the most important ternary operation we run into in terms of its importance of application. So the axioms on betweenness are all intuitive and straightforward. If B is between A and A, then A is identical to B. That is a kind of analog of anti-symmetry for simple orders. This axiom 2 is a kind of symmetry property that reflects we can order either way, starting with A or starting with C. So if we have B between A and C, then it follows that B is between C and A. Third, we begin to get some of the order properties laid out on the line. If, as we've shown in the picture, we have B between A and C, and we have D between B and C, then B must be between A and D. Notice that though we can flip these around, when we get A, B, and C here, from the first relation, when we come to B, D, and C, we couldn't put C on the other side of B because B and C has already been fixed. We could, of course, written the whole thing the other way by putting C where A is, but then everything just flips over. So there's only one possibility here, namely B has got to be between A and D under these two hypotheses. The important thing to check in between is that that kind of interlocking takes place, even though we have in the individual triple always this possibility of inverting the order from left to right. Axiom 4, if A, B, C, that is meaning B between A and C, and B, C, D, meaning C is between B and D, then if B is not equal to C, which I've drawn here, then it must follow that B is between A and D, that is A, B, D. And again, you can check that there's no other possibility of left to right inversion on one of on this final triple that would change this, change how B came out. Well, I haven't said that very well. What I really have in mind is that we couldn't write this another way, given this order. The fifth axiom, just as a generalization of connectivity, reading as I have now, and it's rather easier, ABC, meaning B is between A and C, then we have to have one of the three possible orders, ABC, or BCA, or CAB, for any 3 points on the line. And finally, axiom 6, the axiom we've already discussed in ordinal measurement, simply taken over to the case of betweenness, there exists a finite or countable order-dense subset. We then have as a representation theorem, in a very straightforward proof, the proof proceeds by just fixing arbitrarily a left-right order and then using the results for simple order to get the representation, and then showing you can go either way. There exists a real valued phi such that ABC, if and only if phi A equal to or less than phi B equal to or less than phi C, and then what you can show is, or it could always be for a given triple the other way, phi C equal to or less than phi B equal to or less than phi A. And that's a neat and simple representation theorem. It just generalizes by having the inequality go either way in terms of A and C, just generalizes in a natural way the representation for a simple order. And the uniqueness result has the same flavor, namely we get uniqueness of phi up to a monotone transformation. That is, that monotone transformation can be either strictly increasing or strictly decreasing. Now, we already said something about betweenness as the fundamental concept of affine order. And we discussed in the last lecture briefly separation as the fundamental concept of projective order. One of the things we want to see now is, we didn't go into at that point, is that why in the projective case we can't use betweenness as the order relation. The answer is that when we apply a projective transformation to betweenness, projecting one line from a point of perspective onto another line, betweenness doesn't stay invariant. And let's examine that. So we start with a line in which we have A, B, and C in the order, so it's A, B, C, B between A and C. We take P as a point of perspective, and we take another line in which P doesn't lie, this line right here, and now we project through P each of the points. That means we draw CP to get C prime, we draw PB to get B prime, and we draw PA to get A prime. But we see at once, when we do that, this projection, that we now have B prime, A prime, C prime. That is, B is no longer between A and C, but B prime is out to the end here, and A prime is the middle point, so that the property of betweenness was not preserved under projection. Consequently, we need a stronger notion of order, and we need the concept of separation we talked about last time. And we can see, let's add a point D here, and then let's draw D prime. And let's examine what we have. Well, separation is all right because we have originally AC separating BD. And of course, symmetrically, BD separates AC. And let's check now. If we take A prime, C prime, does that separate B prime, D prime? Yes, because between B prime and D prime lies one of the points A prime or C prime. And correspondingly, B prime, D prime separates A prime, C prime. So separation is invariant under projective transformations. It's true I've only given an example here, but this example, this drawing, shows the flavor of betweenness not being invariant and separation being invariant. So in the projective case, it's separation that we're interested in. Now, it's quite possible to have, and we have in the chapter, a development of the axioms of separation and representation theorem corresponding to what just stated for betweenness. But in the interest of time, I'm going to omit those developments. We won't state the axioms or the representation theorem. But I think those of you who are interested in concepts of order will find it useful to take a look at that material. One of the reasons is that the pure axioms for separation are not too widely used and known. In the case of measurement, it's of course interest because we have this interest in studying underlying concepts of order. I think you'll find it interesting to look at the axioms for separation, which are somewhat more complicated, but not terribly so, in relation to the axioms for betweenness. Now, what I want to go on to is the great classical case of the projective plane. And following very standard developments, we shall initially not consider axioms for separation. We won't have any order on lines in the projective plane. So we'll just take then the following setup. We have two geometrical objects and one relation. So we'll take as geometrical objects lines and points. This gives us the kind of linear variety of objects, varieties of objects we discussed in the previous lecture. And then, corresponding to what we already have discussed about projective geometry in the first lecture, the single relation will be the binary relation of incidence. A point is incident to a line, and completely dual, a line is incident to a point. So we just have then a basic set. We have a subset of lines and a subset of points, and this binary relation of incidence between points and lines. Now, in stating the axioms, it's in the spirit of measurement structures to use operations when it's natural and intuitive. And here there are two operations in projective geometry that we can define in terms of incidence that are worth introducing to give us a simple operational sort of form of the axioms. And the first operation is simply 2 points determine a line, and then the dual 2 lines determine a point. Notice that this duality, of course, as I remarked in the first lecture on geometry, is what makes the spirit of projective geometry simpler than the Euclidean case. Why? Because any two lines determine a point. And of course in the Euclidean plane that's not true. Two parallel lines do not. It's because we consider points at infinity in the projective case that we can have this complete duality between points and lines. Let's see how we can define those two. Let's take the definition of 2 points determining a line. So and I might say I'll use here now as indicated here lowercase Roman letters throughout this discussion, lowercase Roman letters for points, and to distinguish matters, lowercase Greek letters, alpha, beta, gamma, for lines. That notation will make things a little more readable. And it's the notation used in the chapter. If point A is not equal to point B, then AB, and this operation of determination of a line, we just use juxtaposition like multiplication, then AB is equal to alpha if and only if what? A is incident with alpha and B is incident with alpha. That is, point A is incident with line alpha and point B is incident with line alpha. Now it's easy to see how to write down the dual, and let's do that because when we later come to the axioms, I always want to write down only one axiom and not the pair. So all we do is automatically interchange points and lines. So instead of AB, we have alpha not equal to beta, the two lines alpha and beta. Then alpha beta, that is the juxtaposition of these two, this operation of determining a point, alpha beta is equal to point A if and only if alpha is incident with A and beta is incident with A. So notice that it's automatic and mechanical in a completely direct and simple way if you're given one axiom to write down its dual, where we simply interchange the role of points and lines. Notice, of course, we'll read incidents either way. So we can say alpha is incident with A, or we can also say A is incident with alpha. So these two definitions of these operations we'll use in having the operations available and formulating the axioms. Another piece of notation that's convenient is to have 4 points or 4 lines or 3 points and 3 lines not equal, all distinct, not identical or all distinct. So we write not NE meaning in terms of mnemonic, not equal, A, B, C, D. Means all 4 are distinct. So if we wanted to write that out, we would say what that means formally is A is not equal to B, A is not equal to C, A is not equal to D, B is not equal to C, B is not equal to D, and C is not equal to D. So let's now turn to the axioms for the projective plane, realizing that though there are 8 axioms, we only need to state 4 because we take the dual of each of them. So let's state informally our axioms for the projective plane. The first axiom is familiar from what we've already said, namely if point A is incident with line alpha, then alpha is incident with line A. The dual, of course, just goes the other way, which I won't formulate here, A1 prime. If alpha is incident with A, then A is incident with alpha. Axiom 2, what we use in the definition of the operations, if A and B are 2 distinct points, then they determine a unique line. As stated here, then there exists a unique line alpha such that A is incident with alpha and B is incident with alpha. That's a misprint there. Shouldn't be beta, but alpha. And the dual is obvious. Now, the geometrically important and subtle axiom, Desargues' theorem, if 2 triangles are perspective from a point, they are perspective from a line. First question is, why is this axiom called a theorem? Well, the answer is very important and significant. Once we go to more than 2 dimensions, this axiom can be proved. It cannot be proved in 2 dimensions with the other standard axioms, and has to be assumed. Now, let's make a rough sketch of this and then look at a more exact drawing. let's take a point of perspective P, and we'll draw simply 3 lines from that point. We'll pick a base for a triangle, and extend that point out here. Pick another base, bring this down here. Gives us another line for a triangle. And then we construct the 2 triangles like this. I'm only going to do it roughly because I'll show you a drawing that's better. And we have an... Now, roughly drawn, these 2 triangles are in perspective. Why? Because this point of the first triangle and this lie in the same line of perspective. This point here lies the same as that, and this the same as that. And what that now says is that when 2 triangles have this relation that I've drawn, then they're also perspective from a line. And let's see what that means. Now, rather than draw all the lines, let's show how, given this situation, we go ahead and construct lines that construct 3 points of intersection that must lie in a line. That's what perspective from a line means. So I've drawn here something very similar. Here's the point P. That's perspective. Here is the first triangle. And here is the second triangle. And you can see the perspective starting with P. Here's one vertex of that triangle, another one, and one of this. Vertex of this triangle, vertex here, and vertex here. Now, if we extend this line and extend this side of the triangle, we get this point. If we extend, now let's go up and take this side and extend this side, they intersect here. And now we take this side and this side of the second triangle, and they intersect here. And now the important and subtle thing about Desargues' theorem says that given that the perspective from the point P, then the 3 points of intersection that I have made very visible here must be collinear, must lie in a line. And you can see from the construction that that's true. Now, I think the beautiful and subtle thing about these projective constructions, one can only use a straight edge. No compass, no measurements, only a straight edge. And one gets this very beautiful result just with a straight edge pictorially. And that's a fundamental assumption. The dual axiom, of course, just goes the other way. If 2 triangles are perspective from a line, they are perspective from a point. The 4th axiom, informally stated, is the dimension of the space is at least 2. Notice that from axiom 2 prime, we know that the dimension is at most 2, because axiom 2 prime, the dual of axiom 2 I've written there, 2 lines determine a point uniquely, and that wouldn't be true in 3 dimensions. For stating the representation theorem, we need a concept mentioned in the first lecture, namely the concept of a division ring. Remember that a division ring F is just like a field, but multiplication is not necessarily commutative. And in the case of the projective plane, we'll want to talk about the 2-dimensional homogeneous coordinate system over a division ring. So I'll call that H sub 2F. Points are certain equivalence classes of 3 tuples, homogeneous coordinates of the kind we talked about earlier. I'm not going to go into the details here. They're written down in the chapter. But then the fundamental representation theorem for Desarguesian plane, that is a plane satisfying Desargues' theorem, and of course the other axioms, is that it's isomorphic to a coordinate system or an analytical geometry over some division ring F. And that's the fundamental representation. That's why in this geometrical framework, as I pointed out in the last lecture, and as we say in both chapters, the concept of a division ring is important because of this fundamental representation theorem for the projective plane. There should be projective plane in here for Desarguesian. Now, an interesting and fundamental question, settled really decisively by Hilbert, is what is the geometric relation between the division ring being a field and the geometric properties of the plane? Well, there's a beautiful answer. Let's first consider a definition, which again I'll show geometrically in a picture and not write out as it is in the chapter. We say that a Desarguesian plane satisfies Papez's proposition if and only if, again I'll just sketch the example and then look at a better picture. If we take two lines, alpha and beta, and we take 3 points, A1, A2, A3 on the first, and any 2 points in the order shown, B1, B3, B2, and B3 on the line beta. And now we draw from A1 lines to B2 and B3. From A2 we draw lines to B1 and B3. Notice we omit B2. And from A3 we go to B2 and B1. Then if we look at the intersection of the B1, A2, A1, B2 line, that's this one here, correspondingly for the others, this one here, and this one here, that is the A3, B1 line, we can show that these three lines must be collinear. So Papez's proposition is, under this construction, the 3 points I've starred are collinear. And here's a little better drawing of that. Over here, we had alpha and beta, and then the points C1, C2, and C3 are collinear. Again, it's a beautiful proposition, not one that, if you're just thinking about the construction and not doing something with it, is not at all obvious that that in the ordinary plane, of course, that we draw with is Desarguesian, satisfies Desargues' axioms. Then the fundamental theorem is that a Desarguesian projective plane satisfies Papez's proposition if and only if its division ring is commutative. That is, its division ring is a field. And this is the beautiful result that goes back to the beginning of this century. There are additional important things to say about the projective plane, and it's hard for me to stop at this point because I obviously enjoy these pictures and drawings we can make with straight edge, but it's important to go on to the other major topics and leave what I've said as the fragment to be discussed in this lecture. We'll give some other exercises and recommend you look at some of the other results given in the chapter. So one final remark about the projective plane. We get the representation over the reals by adding two more important ingredients. First, we add order in terms of the axioms of separation, and secondly, we add a standard axiom of continuity. Given those two additions, we can then prove that any representation can be obtained in terms of a two-dimensional representation over the reals. That is, a two-dimensional homogeneous coordinate system over the reals. Let's now turn to the next topic, the projective space. Intuitively, we're interested in 3 dimensions for many purposes, but most of what we say extends in a very natural way to any finite dimension. The only thing we really have to add to the concepts of the projective plane is the additional set of linear varieties that come in, namely the set M of planes. I won't state here the explicit axioms for projective space. They're given in the chapter, and the elementary parts are very similar to the kind of axioms already considered. We add to the axioms for the projective plane some additional axioms about incidence, plus the order axioms and the continuity axiom just mentioned. We then obtain as the representation theorem for the three-dimensional case, I'll state it in 3 dimensions, every three-dimensional ordered projective space, not projective plane, that's an output error, projective space is isomorphic to a three-dimensional analytic projective geometry over the reals, where a three-dimensional analytic projective geometry is as defined in the first lecture on geometry. Secondly, the uniqueness of this representation is up to a projectivity as defined, where projectivity is as defined in the first lecture on geometry. So this gives us then a complete melding together of the first lecture on representations and the qualitative axiomizations considered here in terms of projective space. We stated this exact result just for the case of projective space. It really holds for n equals 2, from n equals 2 up. The fact I formulated here for 3 is irrelevant. So that's all we'll say about projective space. Let's go to the next topic of ordered geometry. Here we make a drastic change conceptually. We could, of course, investigate the relations, as we did in some of the remarks in the first lecture, between the projective and the affine case. But from a qualitative standpoint, the natural thing is to begin at the beginning again. We need, in the case of ordered geometry and the specialization to affine geometry, just beyond the set of points A, just a single primitive notion, namely the ternary relation of betweenness, so that the primitive basis is extremely simple for ordered geometry. Let's consider the axioms, because they're easy to state, especially if we use drawings for one or two of the more elaborate ones. The first 4 axioms are just the first 4 axioms stated for betweenness. Remember, I had 6 axioms for betweenness on the line. The last 2 are omitted. The 5th axiom was the connectivity on the line. We don't want that, of course, because we're not on the line. And the 6th axiom for betweenness was a countable order dense subset, finite or countable order dense subset. We don't need that because we'll have an axiom of continuity. So we just have the first elementary 4 axioms on betweenness stated earlier. Then we have axiom 2, a numbering I use here. Axiom 2 is connectivity on the line. I won't formulate that. It's straightforward in terms of the previous axiom 5 for betweenness. Axiom 3 is that we can make an extension. So if we're given any 2 points A and B, then there exists a C. C is distinct from B such that we have A, B, C, that is B between A and C. That's elementary and simple. Axiom 4, if A is not equal to B, these are all points, C is not equal to D, and CD are on line AB, then A is on line CD. And that's obvious geometrically, as you can see here. We have A and B, distinct points, and we have C and D. C and D obviously lie on line AB. And then it's obvious in the ordinary case that A lies on line CD. Axiom 5 is the only really interesting geometrical axiom in a certain sense. That's Pasha's axiom. We're given a triangle, ABC. We're also given point D, such that we have BCD. And we're given point E, such that we have AEC. We now draw the line DE. The axiom requires that there exists a point F, such that F lies between A and B. So we have AFB. And again, in the standard plane, we expect that property, but it cannot be established. It can be shown to be independent from the other axioms we considered. Axiom 6 is just the continuity axiom. This can be stated in a Dedekind form or some related form that I haven't stated explicitly. It's given, of course, formally in the chapter. And finally, we have always to select a dimensionality axiom to determine the dimension of the space. Intuitively, if we're in 2 dimensions, we want an axiom that says all points lie on a plane, but not on a single line, etc. For such ordered spaces, or ordered geometries, we'll sometimes say, we can prove a representation theorem in terms of betweenness over vector spaces. We'll call that numerical betweenness. We have vectors x, y, and z, and in a completely Cartesian or analytic representation, we can think of the vector x as being a triple of real numbers, y, z is same, etc., then y is between x and z if and only if there exists a real number alpha in the closed interval 0, 1, such that y is equal to alpha x plus 1 minus alpha z. That is, y is the convex combination of x and z. It's in terms of that numerical betweenness we can get a representation. In particular, we have the following representation theorem for ordered geometric space. Every n-dimensional ordered geometric space is isomorphic to an n-dimensional ordered space over the field of real numbers. I should remark that if we were not interested in the theory of measurement, most of these theorems we would prove without the restriction of the field of real numbers. One of the important things that Hilbert did in the foundations of geometry was to separate out the role of continuity. And if we drop continuity, then we get a representation over an arbitrary field that is not necessarily a field of real numbers. From ordered geometry, as we've defined it, satisfying the axiom stated, we now get affine geometry. Affine geometry is discussed in the first lecture on geometry by adding Euclid's axiom. Informally formulated, Euclid's axiom just asserts the following. Given a point A and a line alpha, such that A does not lie on alpha, then there exists at most one line through A in the plane A alpha, such that that line does not meet alpha. Notice the stronger axiom would be there exists exactly one for the exact parallel. All we need in this axiom, though, is at most one. If we add then Euclid's axiom to the ones we've already stated, we have the ordered geometry now becomes an affine geometry or an affine space, and we can prove the classical representation theorem. Every n-dimensional affine space is isomorphic to an n-dimensional affine space over the reals. Moreover, for a given n, that is a given dimension, any two such affine spaces are isomorphic. So in that sense, the axioms with Euclid's axioms added are categorical. Furthermore, the uniqueness is simply that up to an affine transformation as discussed in the first lecture on geometry and is discussed also in both chapters. Notice an interesting thing about this now, about the isomorphism. The isomorphism is just in terms of betweenness. As we go on to absolute geometry, we add to the axioms congruence and then add axioms on congruence. We no longer get this categoricity result because we'll have two different kinds of absolute space, Euclidean and hyperbolic. So the categoricity here that I referred to in the representation theorem is just that for the notion of betweenness, not when we add on an additional concept. What I want to now turn to is the specialization of affine geometry obtained not by adding further axioms of betweenness. In a certain sense, what this result shows is that in terms of representation over the reals, given the categoricity of the result, that is that there's only one affine space over the reals up to isomorphism, we can't add any further axioms in terms of betweenness that are interesting. But we can add other concepts. And to get absolute space, and therefore Euclidean and hyperbolic space as special cases of absolute, we add the fundamental concept of congruence of segments. And let's turn now to the discussion of absolute space. Let's now turn to the axioms for absolute geometry. We add to ordered geometry congruence. To clarify a point of what I said earlier so as not to be misunderstood, absolute geometry is not a specialization of affine geometry. That takes us to the Euclidean case, but is a specialization of ordered geometry, adding the concept of congruence. We'll see how Euclid's axiom, which takes us from ordered to affine geometry, plays a role here also. So we add then to the axioms for ordered geometry the following axioms about congruence to get an absolute space. The first axiom just says if BC, that is, we'll think of it as the segment BC, or the distance between the qualitative distance between the points BC is the same as the null distance between A and itself, then B is identical to C. The second is the axiom of symmetry on equidistance or congruence. AB is congruent to BA. The third is transitivity of congruence. AB congruent to CD, and CD congruent to EF, then AB congruent to EF. Axiom 4 has an obvious kind of additivity property, which I've drawn up here. If we have ABC given in that order, that is B between A and C, and A prime, B prime, C prime, and we're given that AB is congruent to A prime, B prime, and BC is congruent to B prime, C prime, then we can infer that AC is congruent to A prime, C prime. So that's like an additivity axiom for congruence. Axiom 5 is a form of an axiom for laying off unique segments. If I'm given a segment CD, remember when I talk about segments and like here, intuitively that's all just a pair of points. So we don't have the formal notion of a segment, but it's a natural geometric way to talk. If we're given a segment CD, and we're given a half line with origin A, and cap A for the half line or ray, then the axiom says there exists a unique point B on that half ray starting at A, such that AB is congruent to CD. And the formal statement of that, without using the concept of half ray, is given in the formal statement of the axiom. But the intuitive content's quite simple. By the way, I should mention that this idea of laying off segments, as we have here, can be taken together with the intersection of segments as a primitive concepts for geometry of the plane. When we do that, we get for the geometry of the plane then something that's sometimes called a geometry over a Pythagorean field. Pythagorean field is just a field in which Pythagoras' theorem is satisfied. Axiom 6 is formulated in terms of points and therefore segments, and it essentially is in a way that gives us the extension to get angle congruence. We're given two congruent triangles, ABC and A prime, B prime, C prime. We now extend BC to get D and BC prime to get D prime, such that we assume that BD is congruent to B prime, D prime. We can then infer that AD is congruent to A prime, D prime. And from that, it's easy to get a construction for angle congruence. So those are the axioms of absolute geometry beyond those for ordered geometry or ordered spaces. And now we have in the case of absolute geometry a rather unusual situation mathematically, in the sense that if we add Euclid's axiom, we get Euclidean geometry, and if we take its negation, we get hyperbolic geometry, and those are the only two geometries we get. So to speak, if we take the absolute geometries, we divide them into two categorical classes, the Euclidean geometries and the hyperbolic ones. So absolute space is said to be Euclidean if and only if it satisfies Euclid's axiom. That's Euclid's axiom, as I just formulated it earlier a few moments ago, for affine spaces. So notice how the picture fits together now. We get back to affine space, in this case, by Euclid's axiom. But we have more, of course, because we have congruence. The point being that if we were taking a progression, ordered space, affine space, Euclid space, then we would just rearrange the order of these axioms. Now, when Euclid's axiom is not satisfied by an absolute geometry, as I've emphasized, we get hyperbolic space. For the Euclidean case, we get the standard representation theorem using just the concepts of betweenness and congruence, or equidistance for points. And we get uniqueness up to a similarity as defined in the previous lecture and in the first earlier chapter on geometry. I won't state those matters formally. They're fairly standard and are written out in the two chapters in detail. In the hyperbolic case, that is where Euclid's axiom is not satisfied, we get a representation isomorphic to the Klein space over the reals. Now, the Klein space is one kind of representation, classical, discovered by Felix Klein, the German mathematician I've mentioned in the previous lecture in terms of the Erlangen program, discovered in the 19th century. The Klein space is gotten by taking the interior of the unit sphere in n dimensions for the n-dimensional hyperbolic space. And then lines in that space are simply the chords without the endpoints of the sphere. And we use that construction of this sphere and these chords in order to go ahead and give a fairly natural definition within that setting of betweenness and congruence, which I won't give here. But we then get one kind of representation of hyperbolic space. It's important to realize that's only one geometric representation. We can get others that are, in a certain sense, spatially more natural, that correspond to our physical space being hyperbolic. I mentioned the example of our physical space being hyperbolic because that way of looking at hyperbolic space, that kind of model, where we now want to have a representation in those terms, is what we want to think about when we have a discussion in perception and an analysis of whether or not visual space is Euclidean. When we ask, is it hyperbolic, as some people have maintained, and as is discussed in some detail in the chapter, but we don't have time to consider those discussions here. It's important to think of the space not in terms of a Klein model, but in something very close to the Euclidean model. The final topic of this lecture is a famous problem in the history of geometry, one of the most famous, the Helmholtz-Lie problem. The famous physicist, physician, and psychologist Helmholtz claimed that physical space has a property that general Riemannian spaces don't exhibit. That is, the property of free mobility of rigid bodies. We can move a rigid body about in the space without distortion. Good example of getting a distortion in a space, if we tried to put a balloon or a rigid body, a balloon's not a rigid body, but put a rigid body that we can squeeze but is rigid through a small tunnel, then that tunnel space wouldn't give us a space of free mobility. So that ability to move a rigid object around any way we please without distortion is a very natural and intuitive part of classical physical space. General Riemannian spaces don't have this property. What Helmholtz wanted to get at is that by adding this intuitive property plus some other rather natural axioms, we would get a characterization of ordinary space. A characterization that proceeded from rather different intuitions on the surface than, say, the classical axiomatizations we've just been discussing. Roughly speaking, the four axioms that Helmholtz proposed is that we start with an n-dimensional manifold that has certain differentiability properties, fairly strong ones. We assume the space is a metric space, as we talked about in the last lecture. With motions now, the concept of motion being an isometry, that is a transformation that preserves all distances between points. Third, that we have this important property of free mobility of rigid bodies. And fourth, a somewhat technical axiom I won't discuss here, the monodrony axiom, that is, a motion should be periodic and not spiraling. Now, we have very beautiful results on this problem. It has a long history of an effort by many well-known mathematicians of the last part of the 19th century, such as Suppes, and in the 20th century, such as Hermann Weyl, to characterize spaces satisfying these properties. Now, one of the modern efforts has been to eliminate the differentiability assumption. And in the detailed discussion of the first chapter on geometry, there's a characterization of G spaces taken from Boosman and other authors. And we have a very beautiful result for G spaces that's a little more restricted, by the way, than need be to get the full strength, the best possible result. But G spaces are rather natural spaces with some topological assumptions and a metric, but not differentiability properties. For dimensions 2 and 3, we have the following result. So we have a G space of dimension 2 or 3, such that we have the following motion possible, that is rigid motion, such that for any 4 points A, B, A prime, B prime, with the distance between A and B the same as between A prime and B prime, there must exist a motion, phi, such that phi carries A into A prime and B into B prime. Whenever we have that situation, and that is enough of free mobility, as characterized here, to then prove that the G space, A, must be one of the 4 following elementary spaces: Euclidean, hyperbolic, spherical, or elliptic. We haven't discussed elliptic in the lecture, but it is discussed in the chapter. And this is a modern solution in very detailed and explicit form of the Helmholtz-Lee problem. I just want to emphasize that the best results are in the obtained in the 50s by the Belgian mathematician Jacques Tietz and the Dutch mathematician Hans Freudenthal, and the best results are somewhat stronger than what I've stated here, but this very much gives the flavor of this classical Helmholtz-Lee problem. And what is important about this is that the very intuitive notion of mobility, of free mobility of rigid bodies, one of our most basic intuitions about physical space as we ordinarily experience it, plays a fundamental role in this characterization of the nature of space from which we get this characterization. In the chapter discussing axiomatic geometry, we also consider, as I've indicated, applications. There is a discussion there of physical space and also a discussion of perceptual space. Unfortunately, we do not have time in this lecture to consider those details, but the kind of apparatus we've discussed here is used. In the case of the physical spaces, we use directly the concept of an affine space. And in the case of perceptual space, we use directly the concept of a hyperbolic space.